Now that we've set up a basic example, we'll talk about how to pass data to the shader programs. Most of this is done in the form of buffers, which are blocks of memory used to pass information between programs, devices, processes, etc. The majority of our CPU side code will be using the tools we just created to package up data into these buffers, define the buffer's shape, and send it to the GPU. In a broad sense, this mostly looks like creating some data we want to send to the GPU, creating a container buffer and filling it with that data, creating a layout that defines the shape of the data we just put in the buffers, and binding this data to a draw command during a render pass. The first buffer we'll be looking at is the Vertex buffer, which is a block of data that acts as a direct input to the Vertex shader. Vertex buffers usually represent a list of data for multiple vertices, so they're organized into blocks of repeating structures that get distributed across Vertex shader invocations. The size of each block is determined by the buffer's stride, which is how many bytes are incremented before passing the memory address to the next invocation. We can choose to increment this address per vertex or per instance, depending on whether we want the data to be more associated with vertices or more associated with object instances. The buffer is just made of raw bytes that get split between invocations, so each block needs to be subdivided into variable bindings that the shader can use for calculations. To create a vertex buffer, we need to start with the data we'll be drawing. We'll once again mostly be drawing triangles to not distract too much from the rest of the code. We're going to create a structure called Vertex that will hold our vertex variables. The buffer expects the data to be in the form of a byte array slice, so we'll use the cast slice function from the bytemuck crate to make it more simple for ourselves. In order to use this crate, our structure will need to be represented as a C structure in memory and derive the traits copy, clone, zeroable, and POD. POD stands for plain old data, which means the structure is just meant to hold data and doesn't have extra behaviors. With that done, we'll also create a structure called example object, which will contain our vertex buffers and vertex buffer layouts to hopefully make these examples a little more readable. First, we'll make a few vertices to form a triangle, then we need to create the buffer and fill it with that data. We'll do this the manual way first, the simple way second, and third, we'll create an empty buffer and write to it with the write buffer function. This last one will show how we update and alter existing buffers. When we create a buffer, we're allocating a block of memory for the GPU to use for a specific purpose. On creation, we'll tell the program what size buffer we want to create, what we are planning on using it for, and whether or not we're creating it with its memory addresses mapped to the CPU space for initialization. Our vertex buffer will be the same size in bytes as the data we've just finished creating. We'll convert it to a byte array slice with the bytemuck cast slice function and use the length as the input. Our usage will include vertex for vertex buffer, and we'll set mapped at creation to true so that we can copy the data to it. We'll get a mutable handle to write data to our buffer in the form of a buffer view by using getMappedRangeMute on a full slice of the buffer. Using this view, we'll copy our byte array slice to the buffer, drop the view from scope, and unmap the buffer from the CPU. If the buffer is mapped to the CPU, we'll get an error if the GPU tries to access it, since we'd possibly have indeterminate data from multiple sources writing to it at once. We can skip quite a bit of this setup process by using the device createBufferInit function, which lets us pass in a byte array slice and usage, and it will just sort out the rest. This is much more simple than the above, but knowing the more manual version as an example will give us better insight when working with the buffer operations in the future. The third way is to create the uninitialized buffer in the same way as the first buffer, but also adding the copy destination flag. Instead of dealing with the mapping functions, we'll instead use the queue-object's writeBuffer function to copy the data for us. We'll also have to pass a queue-object to the function along with a device to use this. This is more commonly used to update or rewrite buffers rather than initialize them, but I figured it's worth showing here. We created a buffer, but we still need to create a layout for it in order for the shader to be able to bind variables to it. Each vertex is described by one instance of our vertex structure, so the size in bytes of the structure we created earlier will be the stride between each shader invocation's starting memory address. These are vertices, so our pointer increment happens per vertex, not instance. Lastly, we'll map our structure's fields to the attributes for our variable bindings. Our vertex structure was storing a position value represented by three 32-bit floats, and a color value also represented by three 32-bit floats, so both values will use float 32 by 3 as their variable format. We'll bind the value starting at byte 0, that is to say our position value, to binding 0, which maps directly to the shader variable binding marked with the location 0 shader attribute. Our color value is located just after our position value in memory, so we'll point the program to the byte just after three 32-bit floats in memory for the start of our next variable binding. We'll use location 1 for this binding, which maps directly to the variable shader binding marked with the location 1 shader attribute. We'll store the vertex buffer and vertex layout in the example object structure for the next steps. In order to use the buffer to draw, we need to add the layout to the create render pipeline structure under the vertex state buffers section and set the vertex buffer on the render pass section. The first argument of the set vertex buffer function is the position of the layout in the buffers array that we just set in the pipeline. With those steps done, we need a shader to run everything. Our vertex input will be our two variables that bind to the vertex shader locations we declared earlier. Location 0 binds to the position value, and location 1 binds to the color value. We'll also create a structure for the output so we can return both the position and the color from the vertex shader and send them to the next shader stages. The location attribute also allows us to pass data from the vertex output to the fragment input, and this pipeline is independent of the vertex buffer to vertex shader input location values. This means that location 0 between the vertex shader output and fragment shader input is not at all related to and does not overlap with the location 0 between the vertex buffer and vertex input. All that being said, we'll set the color to be bound to location 0, which will interpolate the vertex values and send them to location 0 of the fragment shader. We can use this structure as the input of the fragment shader since the syntax is the same, though the position is now in pixel coordinates and the color is now per fragment. In the vertex shader, we'll convert the position to a 4-dimensional vector from a 3-dimensional vector and pass the color input directly to the next step. Lastly, in the fragment shader, we'll just return the interpolated color value. With that, we should see an RGB triangle on screen when we run the program. With some quick modifications, we can add instances in a similar way to what we did before. We'll generate some XY position data to offset each triangle, a radius value to keep track of the distance from the center of a spiral, and we'll also create a second vertex buffer in the same way as the previous one. We'll create a layout for it with a stride of 12 bytes, that's 3 float 32 values, and a step mode of per instance. The attributes will be a 2D float 32 vector starting at offset 0 and a float 32 value starting just after those two values at byte 8. The shader locations will be 2 and 3, since 0 and 1 are already occupied by the vertex values for position and color. We'll create some output arrays to add the buffers and layouts to, and then add layouts to the pipeline vertex buffer section. We'll adjust the render function to add the second vertex buffer, and then add a few instances. We'll add instance position and radius to the shader inputs at locations 2 and 3, and then add the instance position to the vertex position. We'll also adjust the size by the radius by multiplying the XY components by a scaling factor. This should give us a spiral of triangles from the center. As a quick note, now that we have the potential for multiple triangles with overlapping vertices, we can use indices to save space. If we lay out the data for each individual vertex and then create an array of how they are stitched together into triangles, we can save quite a bit of space on larger models. All we need to do is create a buffer with the index data marked index and use it in the render pass by setting it as an index buffer. The only other difference is that we'll use the drawIndexed function instead of the draw function and pass it the number of indices instead of the number of vertices. We can also add an offset to the index value if desired. All those changes let us draw something like this by using indices, which use about half the admittedly pretty low in this case, memory cost as using full Vertex data. That was quite a bit of information, but we're finally moving on to our other buffers, sort of. All of the other buffers we'll talk about require us to create a bind group and assign them to binding indices in order for them to be accessed by the shader. We can have multiple bind groups which all have their own index, and each bind group has multiple bindings which also have their own index. Each binding allows us to create a variable to bind to the data in that memory location. The syntax is similar to the location attribute, using the group attribute and binding attribute before defining a variable. With that, we'll move on to our second buffer type, the uniform buffer. Uniforms are a type of constant value for shaders. We are free to update values stored in this buffer before and after the render pass in CPU space, but during the render, they cannot be changed by the shaders, and the same data is accessible to all shader invocations. Creating the uniform buffer looks the same as creating the other buffers. We'll use the createBufferInit function, pass it the data we plan to use, and we'll use the uniform and copy destination flags. We'll use this buffer to store the current frame as a float, so we'll pass an array slice containing a frame variable of type float32 initialized to 0.0. We're adding the copy destination flag so that we can update the buffer each frame. We'll create the bind group layout and add an entry for our uniform. The visibility determines what shaders have access to this value. We'll set it to Vertex for this example. The binding type will be buffer, and the buffer binding type will be uniform. We'll also create the bind group itself, which uses the layout we just created. We'll add our uniform to the bind group by creating an entry that has a binding index of 0, and the uniform buffer as its resource using the buffer's asEntireBinding function. We'll store the frame variable, uniform buffer, bind group, and bind group layouts in an example object structure. The bind group layout needs to be registered in the pipeline layout, so we'll add it to the createPipelineLayout function in our graphics engine new function. We'll also need to set the bind group in our render function. The index value will be the group index we'll call in the shader. On the shader side, we'll add the variable using the group0 and binding0 attributes, and declare a variable with the uniform keyword. Make sure that the type matches the data you turned into bytes, or you'll get unexpected behavior. Lastly, we'll just need to add it in the calculation. This is the whole process of creating a uniform and using it in the shader, but we aren't updating our frame value to actually count the frame. In order to do that, we'll write an update function that will increment the frame variable and write the new value into the uniform buffer using the queue_writeBuffer function. We'll have to convert the variable to a byte array slice to use it in the function. We'll make another update function for our graphics engine that calls this function and place it after the render function in the redraw request case of the window event function's match statement. With all of that, we have a frame count that we can use as an input to the shader programs. The next buffer type is storage buffers. These buffers can be written to and read from, but writing to the same place in different shader invocations will cause indeterminate behavior. The storage buffer can also hold 128 megabytes, while the uniform buffer holds 64 kilobytes max. These are default values, and they can be increased, but may not be supported on all hardware. This process looks pretty similar to the uniform buffer. We'll create some data, use it to initialize a new buffer, mark the buffer as storage, as well as copy destination and copy source, create a bind group layout entry for it marked as storage and with a unique binding number, and then add it into the bind group. It's part of the same bind group as before, so we're already adding it to our pipeline layout and setting it as group 0 in the render pass. But if we made a new bind group, we'd have to add it to the pipeline layout and give it its corresponding group number in the render pass. The group number must match its position in the render pipeline layout array, or the program will throw an error. In the shader, we'll add a variable with the matching group and binding attributes and add the parameters storage and read/write. Again, make sure the type matches the data inside, or your program won't behave as you expect. To try to make this example simple, the buffer will be sized so that each color channel is a float32 value. We'll index each pixel and set each color channel to its matching index value. In order to actually read this value, we'll have to create a separate buffer to copy the data to. This is due to the GPU and CPU having separate memory to prevent race conditions, but I'm not fully sure what the exact mechanism is under the hood for mapping and copying. In any case, we'll create a copy buffer with the map read and copy destination flags, but this one isn't getting passed to the GPU, so we don't need to add it to the bind groups. In the render function, we'll queue up our render pass and then copy the storage buffer to the copy buffer. This gets added to the queue and we execute the commands. After this, we'll map the copy buffer so the CPU can read it. This is asynchronous, but for simplicity, we'll just wait until it finishes. After it finishes, we'll get the data as a slice and convert it from bytes to float32 values. We'll convert each color channel's float value to an 8-bit value and then save the resulting data to a PNG using an image buffer. With that, we've created a buffer, sent it to the shader, saved the image data to the buffer, read the result, and saved the result to an image file. You may notice that the color is a bit off compared to the image we drew to the screen. The surface is configured to sRGB, standard RGB, which attempts to map the arbitrary color ranges of 0 to 1 to an agreed-upon color space that is both standardized across devices and more closely matches how our eyes sense brightness. The output of our shader goes through a transfer function that maps the linear 0 to 1 RGB values to sRGB, and we can do the same for our image data that we store to the PNG file. You can turn off the sRGB in the configuration options, and you'll get the same dark color scheme in the draw window. I'm going to call it here and save textures as the next topic. It's more bind groups, but I think it might be better to separate it since this video is getting long enough as it is. The code examples should all be on the GitHub in the description. If you liked this video and both want to and have the means to support me, my Patreon is in the description. But it's my goal to keep this free to everyone and free of advertisements regardless of if you do or not. I hope this was helpful or at least interesting, and I'll see you in the next one.